All right, everybody, I think we're ready to get started. So first of all, let me say good evening. My name is Mike Conley, and it's my pleasure to have the opportunity to welcome you to the second installment of the college's Curiosity Drives Progress lecture series. I also want to particularly thank you for tolerating whatever traffic nightmare that you had. How many of you found that life was a lot easier before 35 was a disaster? I certainly did. But in these lecture series, we feature 3 faculty members presenting work related to a larger theme. Tonight's theme is enhancing safety and security. The final lecture of 2018 will take place in September and will focus on the theme of enabling technologies. Through these lecture series, it's an opportunity to showcase some of the remarkable talent that we have at the University of Minnesota, both in terms of the experienced staff and emerging talent alike. Now, due to family emergency, Suraj Dopal could not make it this evening. We're fortunate to have Dr. Tariq Samad, Director of Graduate Studies for the Master of Science in Management of the Technology Program, and an adjunct faculty member in the Department of Electrical and Computer Engineering, presenting in Dr. Dopal's place. So, just a little bit of introduction for me. I have multiple connections to the university. I graduated in 1983. In the College of Science and Engineering under a different name at the time in the program called Mechanical Engineering. I also serve with numerous University of Minnesota folks on the board of Fairview Health Services. I'm also on the advisory board of the Dean of College and Science and Engineering, and last year my daughter graduated from the Carlson School, so I'm connected to this institution a number of different ways. At the same time, as someone who's a technology leader as the Chief Technology Officer of Optum, and I think most of you are familiar with Optum. It's a part of United Health Group. Optum is about a $120 billion business, part of United Health Group, and we are one of the largest employers in the Twin Cities and one of the most actively seeking employees in the Twin Cities. I can tell you that the University of Minnesota is a wonderful place for us to be able to get students with a connection to this community who also have had an opportunity to have a world-class education. That's very meaningful to us as an employer, and I think it's very meaningful economically to the Twin Cities, but it doesn't stop there. The inventiveness of the University of Minnesota, of the College of Science and Engineering, includes the pacemaker, a retractable seatbelt, black box recorder, and lots of other things. I always enjoyed when I was a student going through and seeing like the cyclone separators and the other things that were done in this institution. And this really is an institution that's pushing forward the frontiers of discovery and redefining what's possible. It's also an exciting time. Last fall, the college joined the Driven U calendar, the $4 billion Driven campaign, and College of Science and Engineering is over $200 million to its goal to $250 million. So on behalf of the Dean's Advisory Board, thank you to those whose gifts of any size help the college create more undergraduate scholarships, graduate fellowships, develop new and vibrant teaching and learning spaces, and many more. The college could not do what it does without your support. So tonight we're fortunate to have 3 faculty members joining us. There will be short presentations by Cathy French, Tariq Samad, and Michael Whalen, followed by a combined question and answer session at the end of the presentations. Following Q&A, there'll be a reception outside the theater. I don't know if you saw, there were cookies. I hope you didn't take them before. They were for after. So just make that clear. Perhaps we'll put up signs next time. So I'd like to introduce our first speaker. Cathy French is by the way, this is incredibly impressive. Stay with me. Cathy French is a College of Science and Engineering distinguished professor, where she has been a member of the faculty since 1984. I'm sorry you missed me by a year. What can I say? Her research addresses the behavior of reinforced and pre-stressed concrete structural systems, field monitoring of structures, numerical and experimental investigations of structural systems, including time-dependent and environmental effects, evaluation and repair of damaged structures, and development of application of materials. She is a recipient of an amazing number of awards, including the American College Institute, or as we all call it, the ACI, Joe Kelly Award, the ACI Henry L. Kennedy Award, the ACI Reinforced Concrete Research Council Arthur J. Bose Award, and the American Society of Civil Engineers Distinguished Member and Raymond C. Reese Research Prize. I would love to see her trophy case, is all I can say. They have to be some really cool-looking awards. So she is a past member of the ACI Board of Directors and numerous other ACI committees. She currently serves on the ACI 318 Structural Concrete Building Code Committee, for which she has been a member since 1995. Please join me in welcoming Professor Cathy French.
Thank you, Mike. It's my great pleasure to be here tonight and to share some of the things that are our interests, things that we love to do, and that we have always have curiosity in delving into more. So let me try and see if I can pique your curiosity tonight as well. So the topic tonight I have is shake, rattle, and roll, pushing structures to their limits. And I have some structures up there that are some of my favorites. Looking at history, now this plot is not in chronological order, and the vertical axis is showing height of these different structures. So some of the early structures back to the pyramids, you can see whenever you look at pyramids, they look huge to you. Now let's look at some of the more modern structures. And some of these, for example, the Empire State Building reigned as the tallest building for quite some time since it was constructed in 1930 until it was surpassed finally in 1970 by what's now called the Willis Tower, which most of us know as the Sears Tower. And that was surpassed, but I think it wasn't fair because the antenna on the Sears Tower don't count in the height because they weren't part of the architects. Even though it had the highest occupiable floor, it was surpassed by a number of other structures until there's a clear winner, and that's the Burj Khalifa, which now reigns as the tallest structure in the world. It was completed in 2010, and it is at a height of 800 meters, a little over 800 meters, 830 meters. If you think about the IDS building in downtown Minneapolis, you can stack 3.5 of those on top of each other to approach this building. And so when you look at these structures and you think about engineers, to go from these structures to this one, which is mammoth, how do you push those limits and make sure that you're going to have a safe and serviceable structure? And even now, when you look at what's coming, what's next, this actually is a view from the top tower of that building, so you can get a perspective of what it's like to look down. What's coming next, though, is the Jetta Tower. It was called the Kingdom Tower. It's in the process of being constructed. And what's interesting is one of my former graduate students worked on the Burj Khalifa. And there were very few people who knew how tall that building was as you're working on it, because as soon as that gets out, then somebody's already designing the next building to surpass it. So right now, it was going to be a mile-high building, and the ground couldn't quite sustain that, so they're shooting for a kilometer-high building. So if you can imagine, and it's not just challenging for structural engineers, but think of the mechanical engineers, elevators, water in those structures as well. So anyways, what are the modern approaches to structural engineering? These are some of the major categories. One is past experience. So we have some successful projects, learn from those. Another is to do structural and material testing. Another is to develop models, most of which is that we have validated with experiments. So let's look at past experience. Sometimes that doesn't work out so well. Many of you who've had physics have seen this video before. But in 1940, this structure was built. It was nicknamed Galloping Gertie by those who were constructing it, and it lasted for 4 months. And in a large windstorm, it excited the structure through flutter, and you can see this failure of that structural system. At that time, they were thinking of gravity loads, that you can have a long suspension span and have a very light deck. The girder depths were about 8 feet deep at that time. And you can see it was very flexible. They pushed the limits from what they learned, and it wasn't successful. In fact, 10 years after this failed, the Golden Gate Bridge was actually built before this. There were 2 other bridges longer, but they actually ended up strengthening the Golden Gate Bridge. It had a deck as a C shape, and it's not very strong under torsion, and in a large wind event, think of about 100 miles an hour, that was starting to have some problems. So they stiffened up the deck and made it a box shape. So sometimes you retrofit structures to make them work. So let's talk about other ways to make things work. So structural and material testing. And I have a few things to show you here. So for example, now when you're building long-span bridges and you're using federal money, you have to use and see how the structure performs. Not only that, they do an offering for tall buildings, not only for the tall building itself, but how that tall building is going to interact with the other buildings where it's being constructed. In the middle, you can see a large-scale testing facility we have here on campus, the Mass Laboratory. And why is it a rendering? Because it's very hard to get a good picture inside. I'll show you some tests done in that facility in a little bit. The third thing that I want to show you is a shake table test. This is in Japan, and you can see it's large enough to this has motion in all 6 degrees of freedom. Up, down, twist, yaw, in horizontal directions. And there what they were looking at is a retrofitted timber house versus one that wasn't retrofitted to see how it would perform. So you can learn a lot from experimental tests. In addition to that, we do material testing. This is showing concrete in a test frame. There's 2 concrete cylinders stacked on top of each other. And what we're going to do is apply load to the concrete. And I'm showing you a graph. My husband said, don't put in a graph, but I'm showing you a graph of how much this is going to deform versus time. So we're going to apply some load. So I'm going to apply a force at time 0. And here's the force that's applied, and it will immediately squish those cylinders a little bit. It's greatly exaggerated in my plot. And then if I let that force sit there and walk away, concrete has a property of creep. And so if you look at time, what happens is the concrete continues to creep. And over time, that deflection sometimes is like twice what that initial deflection is. So think of the Burj Khalifa as a concrete building, that really tall building. That's estimated to creep over time 2 feet. Now, the first largest concrete structure was in Chicago, Water Tower Place. At the time that was constructed, they had walls and columns in that building where the columns had very high stresses. The load coming to the column, you can think of somebody's high heel as a lot of pressure, versus if you have a flat shoe in a wall, you have less pressure. Well, higher pressure causes more creep. There was estimates in the Water Tower Place that the upper floors would have a 1-foot differential if you use the same concrete in those members because one's creeping more than the other. So what did they use? They used different types of concrete so that the columns would creep less than if they used the same type of concrete. And the Burj Khalifa, what did they use? They used a matter of distributing the stresses so all of the elements would creep at the same amount. Challenges for those who are doing piping systems, you better accommodate those with a lot of bends and elbows. So you have to think ahead to these challenges as you push the limits. This is just showing the peak displacements. The other thing is modeling. You cannot test everything that you're going to build because once you build it, it's there. So what do we do about modeling? A lot of times we do models that are validated with tests to try and extend those results. So here, if you look at this cylinder, what people can come up with are equations to try and model what's going to happen with that material over time. Well, there's a lot of variability when you look at different volumes of material versus surface ratio. A cylinder is going to have a lot more creep because of more surface area versus the 35W bridge. It's going to take a lot longer for that to creep over time. In addition, type of cement, aggregate type, temperature, and also the environment. Moisture will affect it. If you keep it wet, it's not going to creep. So you develop different relationships that need to include the most important parameters. So we have databases that are shared among the community where people come up with new models, new equations to try and better predict the performance. Here's another example of modeling. So this is showing a picture of a structure that I tested in the Mass Laboratory here with one of my students and some colleagues from some additional universities. And here you can look at this structure. We had hundreds of instruments on it, but hundreds of instruments don't cover everything that's important. So how do I understand the behavior if I don't know instruments everywhere? What you can do is build a model that you validate with the locations where you have instruments. And then what you can do is use the model to explore what are those critical regions doing, stresses and things where you don't have instruments. In addition to that, you cannot build a test specimen to investigate everything. So you'll do a few tests. And then what you do is if you have a validated model, you can make changes to those models to investigate different parameters. What do we do for innovations in structural design? When we push structures to the limits, you can think of seismic regions as where you're really going to expect in the life of that structure that you're going to push it to their limits. So I'm going to talk about seismic for a little bit. And actually, the largest seismic event did happen in the mid-continental United States. And when that happened in the New Madrid area back in 1911, it had a large impact all the way up into Canada. It's a rift in the plate, and so it's very difficult to predict. And it happened before there were many people living here. It caused the Mississippi River to flow backwards. But because there weren't a lot of structures back then, people have ignored it. And it's not until recent history people are starting to look at earthquakes in the St. Louis, Memphis area as a design consideration. And so if we think about seismic regions and structures, what has conventional practice been? We want to have life safety. We want to prevent collapse. That's number one. Number two, you have a hospital, you have police, you have important facilities, control centers. You do not want those to be inoperable. Those have got to be operable. Then, after that, we don't care if a structure is damaged, as long as it's not one of the operations centers. As long as people are not injured, economically, it's easier to build a building that you expect some damage. It's cheaper to do that, more economical. So if you can imagine this as a structure, in Minnesota, we have gravity loads pushing down. When you have wind and earthquake, those are lateral forces. And when you look at those lateral forces being applied to my structure, you can look at how much force it carries versus how much it deforms. And if you design that structure to be elastic, it means you'd push it in one direction, release it, it would go right back to the original position, undamaged if it's elastic. That costs a lot of money to design for those big forces. So if you can develop a structure that deforms, you can design it for a lower force, have less steel in the structure, it's more economical. And that means that it's going to have deformation capacity. You don't want it to break here, you want it to deform. The other thing about it is it's going to eat up energy or dissipate energy. What does that mean? My structure is going to be damaged. And so here's an example of such a structure. This is one of my tests in the mass lab of a core wall system. So a lot of buildings have elevators, you put cores around it. This mass system is really the first of its kind to do large-scale testing where you can do multiple degrees of freedom of loading. So this is the wall with inside that building. The system was developed by MTS in Eden Prairie here, and these were the largest hydraulic bearings of their kind. In order to apply large vertical loads, you can put on a load of a 20-story building and test a component. And because of those hydraulic bearings, there's very little friction when you move the structure in multiple directions. So it's an incredible piece of equipment. And let's look at what happened to the structure designed with conventional means. This is what it looks like after that earthquake event. Cracking, yielding, buckling of bars, but the building would still be standing. But it is, in fact, this is showing the force versus deformation. As you load it, it deforms. When you release the load, it ends up offset. And so these buildings would be difficult to occupy. You would have to repair them. So a lot of times after earthquakes, it's very difficult to occupy them. So it has a huge economic impact. In about the 90s is when people started to think we need a new design philosophy. That was with the Northridge Earthquake and the Great Hanshin Earthquake, where this is showing the economic loss in billions of dollars. And what's shown here is a plot where these dollars are adjusted to the year 2012. This was a paper at the 15th World Conference that's giving this data. And it accounts for the fact that if you can't reoccupy your building, you will have to, your business isn't going to be operating. Here in the Hanshin earthquake near Kobe, that's a big export place. A lot of these cranes fell over, so it's a huge economic disaster. Why is it more in Japan than the United States? The population is much concentrated in very earthquake-prone areas, and compared to here in the United States. But this economic impact impacts everyone in the United States, not just the local people. So what do we have for a new design philosophy? It's called performance-based engineering, where if you have an earthquake that you expect, if you're building in California, you expect an earthquake multiple times through the life, make sure it performs well. If you ever get the big one, so if you're designing a structure in Memphis, where the return period might be 500 years, you might not even expect an earthquake within the life. But in that case, you want to make sure it's not going to collapse if the earthquake ever does come. And so the premise is that you can develop these performance levels or objectives, and then rather than just looking at the first construction cost, you should think about the life cycle cost of this building that you're constructing, and you can make a decision on which sort of performance that you want to go for. But in order to quantify these, you need testing to evaluate what sort of cracking, what sort of performance might you expect that's repairable to fall in these different categories. There are also innovations in design philosophy. This is showing a rendering of a test that we did at our Mass laboratory as well, where here, instead of looking at the wall system that we had, this wall is a concrete wall that basically has a piece of steel, like a rubber band, in a hollow tube inside. And when that wall deflects laterally, that wire in that tube stretches. And because it's not bonded, it's not going to yield. It stays elastic and wants to close that crack. And if you look at the response of that system, as that wall rocks, before it picks up, it's very stiff. When it leaves the base, it gets less stiff. If you unload it, it goes right back to the original upright position. What's wrong with this? You don't see much energy dissipation. So what you can do with this is add fuses that are going to help to dissipate energy that are replaceable. With those fuses, you can take that low deformation response and start to eat up energy for your system. So if you look at the system, this is showing my wall. Here you can see one of, we call these O connectors, attached between the wall and an adjacent column. And when the wall rocks, the corner that's staying down, nothing much is happening. But here you can see this O connector is going to be very distorted. It's going to yield and stretch and eat up energy. So you can cycle through and see how that's working. This is showing a figure of that structure in the Mass laboratory as we test it. And so as the structure is going to rock back and forth, let me see if I can get it going again. You'll be able to see the wall rock back and forth. You can see the floor is moving with it. And so what we were interested in looking at this investigation is how does the surrounding structure impact the ability of this building to self-center? And in fact, we did another test where we developed connectors so that the floor didn't need to be picked up with the wall system. So this is comparing conventional practice to that rocking wall system. You can see there's not much damage in that system. And the O connectors are all distorted. Those are the ones that eat up energy. You can replace those after the earthquake event. You can see local damage due to the floor that was trying to be picked up and put down. But again, you can develop connectors so that you can transfer the lateral loads and have it slotted so that the wall can pick up relative to the floor. So what are the impacts of our research? Number one, it's to be able to extend what we're learning into practice. And we do that in a number of different ways. This just shows one example that I love. We work with industry. We work with the State Department of Transportation as an example. And working with those two together, you're definitely impacting them by putting your answers into practice. So for example, in the bridge area, you can explore the use of new materials. Why is that good? You can build longer span bridges. I love this picture. Trying to get that bridge girder that's over 150 feet around that corner is pretty cool. They drive those axles separately. But you can maybe eliminate a pier. That's a lot of cost savings. You don't need to worry about that foundation and that pier in that case. You can improve constructability, looking at systems to try and reduce cracking, and also try and reduce construction costs like 35W, things like that. Oops. This shows also something that I think is fun in our position. We can break things, as you can see, push structures to their limit. Here's a girder where they had made some adjustments, retrofitted in the service, and then when that bridge girder was done, they wanted to compare how does our model predicting the capacity compare to what it actually is. And so there's a lot of energy in those systems. The other thing in terms of impacting practice, as Mike mentioned, is participating on building code committees. So we are the ones who can translate what we learn into code development. And so that also is very rewarding and fulfilling. And not only that, having students involved, the other is we're educating the next generation of engineers. And so having them not just understand what are the rules to follow this code, but how does the structure behave? What are the mechanics of it? Get them involved in research. That's probably one of the most exciting and rewarding things. And with that, I'd like to thank my colleagues in the department and some collaborators at the University, Iowa State University. And with that, I'm going to pass it on to Mike to introduce our next speaker.
So thank you, Professor French. I just must say that was solid. I'd like to introduce our second speaker, Tariq Samad, who holds the Honeywell W.R. Sweat Chair at the Technological Leadership Institute at the University of Minnesota, where he also serves as the Director of Graduate Studies for the nation's longest-running MS in Management of Technology program. Dr. Samad also holds an adjunct faculty appointment in the Department of Electrical and Computer Engineering. Dr. Samad joined the Technological Leadership Institute in 2016 after a 30-year career at Honeywell. During his career with Honeywell, he contributed and led automation and control technology developments for applications in electric power systems, clean energy, building management, the process industries, automotive engines, unmanned aircraft, and advanced manufacturing. His research interests relate broadly to automation and control, intelligence, and autonomy for complex engineering systems. Dr. Samad is a past president of the American Automatic Control Council of the IEEE Control Systems Society. He has received numerous awards, holds over 20 patents, and has authored or co-authored over 100 conference and journal publications. Please join me in welcoming Dr. Samad.
Thank you, Mike, and thank you, Moss, for the invitation to come and talk to you about a topic that I think is very important for our state, our nation, the planet as well. And the topic is smart grids, energy security, renewable energy. I'll be talking primarily about the technology elements behind these areas, these topics, but not in any level of detail. So I won't show you any equations, not even any graphs. But to begin with, what I'd like to do is to just motivate the topic. And a lot of the interest in this area of renewable energy and smart grids started to arise maybe 2 decades ago, and it was a result of 3 particular issues and concerns we had with our energy system. And these concerns are indicated on this slide. So first of all, the first concern is energy security. We want to reduce our dependence on imported oil and gas, right? And At that time, that was a major concern. Since then, of course, we've had the shale oil and shale gas boom domestically. So to some extent, that's been mitigated, but it remains a concern, as evidenced, for example, by the controversies about gas pipelines and oil pipelines from Canada. And down the future as well, of course, we do want to have our own energy sources for everything we do in the country. The second issue is economics. And energy cost for consumers, for industry, for businesses is, of course, a major concern. Again, if you go back 10, 15 years, we had very high prices relative to today for energy. And there were the projections from DOE were for those prices to continue to increase. I remember in I think it's exactly 10 years ago, the retail price, the wholesale price for natural gas was something like $7.50 per million BTU. Okay? Today, it's less than $3 per million BTU. But nonetheless, we all want cheaper energy. We want reliable energy at low cost. And the projections are, again, for energy costs to increase. So that's a second concern. And the third one, the last graph, the rightmost graph on this chart, relates to the energy use, and in particular, the use of fossil energy on the environment. And this has, of course, been a major concern globally for some time now. I started tracking this many years ago, and so this chart is actually relatively recent. And it shows, the data is from the National Oceanic and Atmospheric Administration, and they've collected data over the last 138 years, assessing the global temperatures over that time. And the 10 hottest years globally over that time have all been in the past 2 decades, so from 1998 on. And even worse, the 3 hottest years have been 2017, 2015, and 2016. Okay? So renewable energy and smart grids certainly are no panacea, but they are seen as an approach that can help mitigate all of these concerns. Okay? So we'll talk about that. But the issue is that it's not so easy to just take out all your energy sources, replace them with renewables. Renewables have certain characteristics that make them very different from the sort of energy sources we're used to. And the question is, how are you going to address those? So this chart tries to illustrate what the key difference is in enabling use of renewables compared to traditional ways of running a power system. So the top chart, the top graph, top picture, shows a traditional power system. So what happens in a traditional power system? Well, in a traditional power system, oil, gas, coal, to some extent nuclear as well, you have control over generation. You have complete control over generation. One thing to remember, by the way, whenever you talk about energy and talk about electricity in particular, which is what this chart is about, and most of my presentation is about electricity, is that the one thing to remember is that we have no effective, cost-efficient, scalable way of storing electricity. So in the grid, at any time, at any instant of time, all the electricity that's being generated must be consumed. Okay? Of course, this is a challenge, right? But we've addressed this challenge by being able to have controllable generation. So on the load side, when people flip switches or businesses start equipment, whatever, right? Of course, there's consumption happening. There are effects on consumption happening. At the generation side, that effect on consumption is instantaneously being detected just through the frequency of the line voltage. And based on the detection of the frequency, generation goes up or generation goes down. So that's how we manage to keep the grid in balance, even though we don't really have control over loads, and loads are unpredictable as well. It's because we have perfect control, more or less perfect control over generation. What happens with renewables? Well, now we have wind and we have solar, and we do not have perfect control, and we cannot even in many cases accurately predict the generation that we will get from them. So obviously this creates a problem, right? How are you going to keep the grid balanced? We want to have more renewables. We want to be able to use more wind, more solar power, but the grid has to stay in balance. Well, the only way to achieve that is to now start putting control on the load side as well. Okay? So now we have to have sort of this twinned approach. There's some generation that is still more or less deterministic. There's some loads that are more or less deterministic, but then we have to have flexibility on both sides too. The saving grace here is information and computing and communication technologies. So things like wireless communications, for example, or low-cost sensors, or big data analytics, or cloud-hosted platforms. And we are now entering the age of the Internet of Things, as we often talk about now. That's what we can rely on to try and achieve the control that's depicted in this bottom picture. Okay? And so I'll show you 3 examples of technologies that are being developed for these. Again, they're sort of, the depictions here are not going to go into too much detail. Happy to go into more details if there's time or if there are questions. And in fact, in the first depiction, it's a cartoon, basically, right? So on the left-hand side of the cartoon is something called direct load control. And if you own a house, if you have central air conditioning, many of you are using direct load control already. So Xcel Energy and other utilities have programs where they will put a switch on your air conditioning unit, right? And on certain hot days during the summer, they have the right to cycle your air conditioning on and off. And the effect is the interior temperature of the home is going to be raised by a degree or 2, depending on conditions. Right? And Xcel Energy or the utilities will do that based on whether they're having difficulty keeping the grid in balance or whether they're seeing very high costs for electrical power as well. So that's one approach. But it's a very limited approach, right? It's basically for air conditioning. And perhaps more importantly, it gets the user out of the loop. So the user is no longer in control. The homeowner is not under control. Is not in control of this process. You may be throwing a party. You may have your boss over, and you know, I had a boss who didn't like to be seen sweating. You know, that could be quite a challenge in a case like this. So a much better solution is the cartoon on the right, which is automated demand response. And here, the homeowner is in control. And the idea here is that the utility gives a signal to an energy management system. And this energy management system has been programmed, scheduled, based on the signal being given. The signal could be a price signal, or it could be some other kind of signal too, to turn on and off loads or do other adjustments. This is used quite widely now, especially in commercial buildings where things will happen automatically, like turning on and off non-essential lighting, increasing or decreasing thermostat settings. If you're in a large commercial building with elevators, some of the elevators could be put on hold if energy needs to be consumed. It's also happening in homes in many cases too. But there's actually, we've kind of just scratched the surface with this technology, and more research is needed in order to be able to take it to where we need to take it. And this research includes things like, what is the right signal for a utility to give to get a certain level of consumption change, right? You want a precise level of consumption change, and you may give a price signal, but you're leaving the user in control. Well, you can statistically try and verify that and try and model that, but of course it's an issue. How do you incentivize users to do the right thing in a case like this? How do you classify and categorize the customer base, right? If this is a hospital, it's one thing. If it's a mall, it's another thing. If it's an office building, it's another thing. They have different needs, different types of equipment, and all of that. So many other interesting issues related to this topic. The second topic, microgrid optimization. To get an idea of what a microgrid is, think of the University of Minnesota campus as a microgrid. Right? The University of Minnesota campus has a large number of buildings. Right? It has many devices and loads that consume energy. It has heat and power generation facilities on site. It has some number of electric vehicles now, and in the future we'll have even more of them. And maybe in the future, those electric vehicles, the batteries of those electric vehicles will on demand be providing power back into the facility rather than just being charged. The charge and discharge capability will be there as well. Right? In addition, of course, the University of Minnesota campus is connected to the utility grid. And that utility grid, that connection is being moderated as well and controlled as well. And how much power you get from the utility versus how much power you generate on site is something that could be under your control. And right now, the facility management services at a place like the University of Minnesota will be managing and controlling all of these devices, making all these decisions. They'll use dashboards, they'll use various kinds of tools. But what they aren't doing today is really doing something that could be called truly optimal in some sense. And that's really an interesting area and an exciting area of research. And in order to do that, what do you need? Well, you need to develop mathematical models. You have to have mathematical models of all of the equipment. You have to be able to do some forecasting of the load that you are going to see over some horizon. The horizon might be the next few hours. It might be the next day. It might be over a week. Right? You will need to be estimating some generation forecast as well based on weather patterns. Right? You'll need information about utility pricing structures, which of course you have. And the idea is you have to put all of these into a mathematical formalism and a formulation and crunch that data and crunch those models to get the optimal way to operate the facility, all the while keeping into account the variety of uses or that variety of services and uses that the University of Minnesota must provide, and the diversity of people that are here and their needs as well. Right, all of that those are constraints on the optimization. Microgrids exist now. A well-known example is the federal. The Food and Drug Administration microgrid, their large campus that they've recently constructed outside of Baltimore, Maryland. Honeywell, my previous employer, did the microgrid for that facility. Even in the first year or two, there was substantial savings in energy security, energy reliability, energy cost. The example that's often given is when Hurricane Sandy went through that area, the microgrid automatically detected, just based on fluctuations in the voltage, that there was some problem happening with the grid, and it automatically shut down the non-critical loads, started some generation, some manual effort involved there, did something with some of the loads and the storage that they had, and disconnected itself from the grid. So it islanded itself, and I was able to ride through that storm. And that the FDA facility is a very critical facility. There are many things that are safety critical and life critical that are happening in there, and you can't afford to just have the power go out. But it's really still a big area for research, and much more research needs to be done. I wouldn't, in fact, call that microgrid example I was just referring to as an optimized microgrid. There are some smaller examples of optimized microgrids. I know one that was done with Honeywell at a hospital in the Netherlands. And in fact, by the way, one of the leading researchers in the area of microgrid optimization is Professor Georgios Giannakis at the University of Minnesota. So that's technology number 2. And 3, I'll refer to the work that you were supposed to hear about, and you would have heard about in much more detail and much better than I can do justice to. And that's the work of Professor Siraj Tople on virtual oscillator control. And this work addresses the problem of connecting distributed energy resources that are in homes, that are in buildings, connecting them to the grid. Right? You have solar cells on rooftops. You now have electric vehicles. You have fuel cells coming into play. In fact, the number and the diversity of these distributed energy assets that are sitting in homes and facilities, and not in the utility, that number and type are steadily increasing. One important factor with many of these and most of these devices is that they are DC devices. A solar panel generates DC power. It doesn't generate AC power. Your car battery takes DC input. It requires DC charging. Right? Similarly with fuel cells. So what you have to do in order to connect these devices to the grid, and we want to connect them to the grid because we want these to, of course, feed the grid and be available to others in the grid to use as well, the energy coming from these sources, and conversely too. So these, in order to feed these to the grid, you have to synchronize them. You have to convert the DC to AC, and of course the conversion goes the other way when the charging is happening, and if it's something like a battery, right? So you have to convert the DC to the AC, and then it has to be synchronized with the phase of the grid. Right? And it's a difficult problem, and the current ways of doing it are inefficient, and they have time lags associated with them. It takes quite a bit of time for the power electronics to work and get the synchronization done. So Siraj's idea, and that he's been exploring quite successfully, is taking this notion of nonlinear virtual oscillators. So having a distributed set of devices, power electronic devices that are automatically sensing minute changes in the grid and adjusting themselves in a way that is coordinated without being centrally coordinated, just in a distributed fashion. And that substantially alleviates these concerns with integration of these devices to the grid. And as you can see here, he's shown that you get 10 times faster synchronization of these distributed energy resources with the grid. Okay. So those were the 3 technology vignettes, let's call them, that I wanted to share with you. And now I'm going to go back to the motivations and what's been happening since, right? What's happening since we got onto this road, and of course, much more needs to be done. But are we making good progress? Are we not making good progress? Are the problems still remaining, right? So here's first of all some good news. The left chart shows the cost of energy, in the cost of electricity. In fact, the levelized cost of electricity, and the levelized cost of electricity sort of is a way of normalizing electricity costs. So you're comparing apples with apples and not apples with mangoes or something to refer to a fruit that's been on top of my mind lately. And what you can see from these charts is that wind, onshore wind, and photovoltaic systems, so PV, so solar cells, are now cost competitive with coal and natural gas. And furthermore, that the cost of these renewable generation technologies is going down, whereas the cost of coal and natural gas generation is going up. Right? So this is certainly good news. Right? The second chart, actually, I find this, to me, is particularly, I'm particularly fond of quoting this chart. And hey, look at that. Actually, I do have a graph here. And what this shows is, and we tend to assume that increasing the economy inevitably requires consuming more energy, using more energy. And that often has been the case. There's data that shows that. Historically, it's been the case. But it's very interesting. With all the emphasis on energy efficiency that's coming, that coupling perhaps is being broken. So over the last decade, the GDP of the US grew by 12%, but energy use overall dropped by 3.6%. Right? So if we can maintain this trend, that's also really, really good news. And lastly, you can see some power plant emissions have fallen down as well. But I wouldn't be giving you the whole story, and if I left you with any sort of feel-good notions, all right? So here's the not-so-good story. The right side of the chart you saw already, right? So again, it's showing the 3 hottest years over the last 138 years that NOAA has been collecting data. We're in the past 3 years. Right? The left side of the chart are CO2 readings, atmospheric CO2 readings. And the time axis on the horizontal axis is from 1700 till today. In fact, not till today. I downloaded this chart on June 8th, which was last Friday, so from 1700 to last Friday. Okay? And until about 1958, this data was estimated, the CO2, atmospheric CO2 concentrations was estimated by taking ice core samples. Okay? Since then, there's an observatory instrumentation at Mauna Loa in Hawaii, where on a regular basis, this data is being collected. It's available on the web. You can anytime go and look at it. And in fact, that's how I got this chart here. Right? So you can see that as industrialization progressed, CO2 emissions increased. But most dramatically, after World War II, all the growth that we've seen since then, those CO2 emissions have been really dramatic in their increase. I remember, this is now, again, going back maybe 15 years ago, when the scientific consensus was that 400 parts per million CO2 in atmosphere was really a threshold we should try not to cross. That at that point, the scientific consensus was that we would start to see some effects of global warming. Well, we've blown by the 400 ppm level. We are starting to see effects. And now people are thinking, well, can we maintain it to 450? And what impact is that going to have? Right? So that's why we need more and more research in areas like renewables, like smart grids. How do we reduce the CO2 footprint while we have energy security at the same time and address the economics too? But technology is not the only part of the answer. In all of these areas, we can come up with new devices and new algorithms and new tools and new mathematics and new laboratories. But ultimately, to get impact, you need much more than than technology. You have to think about the business models that would allow these technologies and to be, or products to be made and used broadly. The policies that would have to change. New standards that would need to be adopted. How to do things in a global context, because many of these challenges are truly global context, global challenges. This is a chart that's, by the way, by a colleague of mine at the Technological Leadership Institute, which you'll hear about next, Kirk Frogat, and I kind of like sort of this notion that innovation is not just about technology. It's about more than technology. Often, certainly if it's engineering innovation or scientific innovation, technology is a core piece. But you can't think that that's all you need. Which leads me to my concluding slide. I'm with this organization called the Technological Leadership Institute, and I run a program within TLI called the Masters of Science in the Management of Technology, or MOT. It's kind of like an MBA in some ways, but it's oriented toward technologists. And you may think, why do we need a program that's focused on the management of technology? Well, the quote at the bottom hints at that, right? Technology has a huge impact on the economy. It's not just something we play around with or we develop good devices with or have products with. The impact on the economy is tremendous. So you have to have effective ways of managing technology, of managing innovation, of taking ideas to practice, of figuring out what are the intricacies between policy and society and business and technology and research and all of that, right? So very intricate issues that need to be discussed. Our admissions director, Shea Moa, has a really wonderful blog on our website called Which Shark Are You? Okay, and it sort of refers to the MOT program and MBAs. And neither is better than the other. They both are serving very well certain audiences, the audiences they target, the students they target. But Shea's analogy is the following, that it depends a lot on how you approach new opportunities, how you approach new ideas. If you approach them from the mindset of a Kevin O'Leary, if you've watched Shark Tank, right? So you're really focused on the numbers, you are really systematic and rigorous about the finances, you're asking really good hard questions on that. The MBA will help you answer those questions and help you ask those right questions better than the MOT program will. But if you're approaching it from a technology lens and thinking about the technology piece and interested in that, which is more the Mark Cuban approach on Shark Tank, then we think the MOT program is a good one for you, for students who may be interested. So with that, I look forward to vague and cloudy questions at the appropriate time, and I'll hand it off to the next speaker. Thank you.
So thank you, Dr. Samad, for a very energizing conversation.
Oh, boy.
I appreciate that.
What's he going to say about that?
I'm sorry. It took, it was like 8 minutes to think of that. So I'd like to introduce our third speaker. Michael Whalen is the director of the University of Minnesota Software Engineering Center and a consultant for Rockwell Collins Incorporated. Dr. Whalen is interested in formal analysis, language translation, testing, and requirements engineering. He has developed simulation, translation, testing, and formal analysis tools for model-based development languages, including Simulink, Stateflow, and others, and has published more than 80 papers on these topics. He has led successful formal verification projects on large industrial avionics models, including displays, redundancy management and control allocation, and Autoland. He is currently working on improving the scalability of formal verification and extracting information and proofs that can be used to satisfy certification requirements related to traceability and adequacy of requirements. He has recently applied proof tools toward creating secure autonomous vehicles in the DARPA High Assurance Cyber Military Systems Project. Please join me in welcoming Dr. Whalen.
Thank you. It's really a pleasure to be here. And to talk about how the kind of twisted paths that end us up where we are, and the mechanisms by which I ended up working on security were, quite strange. And how I ended up here was really trying to make systems safer. But it turns out that these two are intertwined in a way, especially today, that they've never been in the past. So let me give you an example of that. So suppose you're out on a nice Sunday drive. You're on a 2-lane road. It's quiet. You're watching the trees go by. And suddenly your radio comes on full blast. And you think, let me get that. And then suddenly, as you're fiddling with the with the radio, the air conditioning comes on full blast. And as you're trying to figure out why your car is possessed, the windshield wipers start flapping back and forth, and the windshield wiper fluid is coming onto the windshield and basically obscuring your view. And as you're contemplating your coolness under pressure, at least you still have control of the car, you realize that you don't, actually. You press on the brakes and nothing happens. You turn the steering wheel and nothing happens. And a few seconds later, you're in the ditch. And this is all because of a hacker working on a laptop hundreds of miles away. Now, this may sound incredibly far-fetched, but it's already happened. So a security researcher named Charlie Miller was frustrated that his concerns about the insecurity of automobiles were being ignored by the auto industry. So he contacted a person from Wired magazine, a reporter, and he said, do you mind if I hack your car? And he gave him the parameters of when this would happen, sometime on a Sunday, and where they should be driving. Apparently the slide timings were left on. This is not so good. Anyway, we will work with it. So anyway, what happened was that they ended up in the ditch, and Jeep ended up recalling 1.5 million cars. Now, this wasn't the first time that cars had been hacked. It had actually been hacked by Stephen Checkaway and some other folks at the University of Washington. And if you thought losing control of your car was the only thing they could do, you're wrong. They can also remotely surveil your car, meaning that a lot of cars have microphones in them now, and you can actually listen into conversations. You can also use GPS to see where you are, and you can steal a car by hacking it remotely. Now, it's one thing to do this to a reporter for Wired magazine. It's quite another to be able to do this to anyone else who owns that make and model of car. And while they targeted Jeep, they could have targeted BMW or Audi or any number of different cars. So, how? How could this happen? Well, the car I grew up with when I first started driving looked something like this. When I pressed on the accelerator, there was a cable that went to a carburetor and caused gas to enter the engine, and by golly, it made it go faster. I like that. Now, the same thing happened for the steering and the brakes, but if you look at a modern car, really it's more like a server farm on wheels. So you have a computer that controls the radio, the anti-lock brakes, the airbags, even getting in and out of the car, the transmission, everything, you name it. When I press on the accelerator now, what happens is that a sensor picks that up, and a few bits go down the wire to another computer that controls the engine, and that computer causes more gas to enter the engine, which is great. I mean, there are a lot of great capabilities that come with this. When I speed up, the radio gets louder. It's like magic. When I press on the brakes, if it's icy, the anti-lock brakes come on. So this is wonderful stuff. But now it's a server room on wheels. Well, we know something about server rooms. What we have now is something that has what security researchers call a large attack surface. Now, this car is not an island unto itself. You have Bluetooth networks that allow it to connect to your iPod. You have OnStar that allows you to go up to a satellite or to a cellular network. And when we look at this, we have lots of different ways that attackers can get in. So, we have auto manufacturers that are building server farms on wheels but aren't really familiar with security. We have a large attack surface. What could go wrong? And what goes wrong is exactly what Charlie Miller demonstrated. So what we want to have trust domains. So there are lots of wonderful things about having computers on cars. We're not trying to get rid of computers. But by golly, we should be able to determine whether this is part of the critical infrastructure or whether it's a nice to have. So when if I'm the brakes, when I receive commands from what I think is the brake pedal, I better be sure it's the brake pedal and not the radio, because we don't want the radio controlling the brakes. So how we do this is 3 different mechanisms. We want to have authentication, that when I receive a command, I know who it came from. Whoops. We want to have encryption, that no one can tamper with the message as it goes across the wire, and finally want to have isolation. So if I know something is likely to be insecure, I want to wall it off from the rest of the system. Well, if we look at the automobiles, what we see is the radio here. And the radio is running a full Linux stack. It's about 33 million lines of code. It has facilities in it for communications with OnStar, with Bluetooth. You can put your iPod or your iPhone on the dash, and it'll just recognize it. It's amazing. But there is no separation. There's no isolation of the radio from the rest of the vehicle. So if, by chance, I'm able to sneak into the radio through OnStar or through Bluetooth, I can pretend to be the brakes or the steering, and the car will not gainsay me. And so this is how attacks happen on modern vehicles. 99% of all the literature I've seen on the subject comes in through this one silly location. That's really not critical to the vehicle's performance. So, and it's bad enough that we do this on commercial automobiles, but on military systems, you really want some separation. And it turns out that they're susceptible to the same kind of attacks. So this is a case in 2012 where Iran landed a brand new US stealth drone on their runway unscathed because they jammed the communications and spoofed the GPS to convince it was over Afghanistan. So DARPA, the Defense Advanced Research Projects Agency, has devoted a lot of resources to try and make this situation better. And what this is a 32-foot Boeing autonomous helicopter called a Little Bird. Now, an attack team got into that Little Bird in 45 minutes. That Little Bird can carry weapons, it can carry troops, it can fly autonomously, and if the hackers are controlling it, not to where you want it to go. So what we were tasked to do was to build replacement software and replacement architectures for the vehicle so that they could no longer control it. And to keep us honest, there was an attack team, the same team that broke in on the initial vehicle, that could ghost our meetings, could listen in our phone conversations. They could get access to all our design information, all our software. And they had 3 months and virtually unlimited resources to break things. They're creepy people. I was sitting at the hotel bar one time, and one of them asked me how Kim was doing. Kim's my wife. They don't know my wife. So how did we approach this? Well, really, it requires a foundational, different understanding of how to construct these vehicles. We need to think in terms of architecture-driven assurance. We have to understand the architectures of the things we're building. So if you want to think about cars, how they were constructed is like barnacles attaching to a ship. So we added additional capabilities, and then we didn't really think about how they were all put together. And so what we proposed and what we worked on in a $20 million effort is this idea of focusing on the system architecture and focusing on software proof in order to really gain assurance of the system. So this was a joint effort by the University of Minnesota, Rockwell Collins, Boeing, Galois, and Data 61. So it involves several pieces. We have to make sure that we understand the architecture and that the critical pieces actually work the way they're intended to do. So the operating system piece, I mean, everyone's familiar with Windows. What Windows is supposed to do is wall off one process from another. And sometimes it does, and sometimes it doesn't. And when it doesn't, we have these security problems that you hear about. And so we worked with a team that actually had a proof of operating system security. And then we had another team that developed control components in such a way that they were hack-proof at compile time. So if they would compile, meaning if there was something, a piece of software you could deploy, then the most common kinds of attacks couldn't occur in them. So let me show you what the architecture was. So this is looking at the Little Bird. So our Little Bird radio equivalent is actually the vision system, where you can track targets on the ground, and you can choose that to set the flight path. And that is running a Linux stack with 30 million lines of code and a bunch of third-party software. And it's not actually critical to the flight control that this works. So if you can't surveil a target, that's bad, but you can still fly home. And so we wanted to wall that off from the rest of the system. And so we built some very high security components that just looked at the communications between this VM containing the camera software and the rest of the critical software. If you think of it analogously, and we did the same thing with cars later on, we jacked up the radio software and put something underneath that says, I don't care what the radio does, but if it ever sends a message that says it's not the radio, then you want to reject it. So this is what we did. But even given that we've architected the system correctly, software testing is hard. It's like banging your head against a wall. And what's worse is it's inherently hard. So the problem with software testing is that unlike most engineering disciplines where you have some continuity to help you with testing, you don't have that with software. So in most systems, you're building a bridge. And you know kind of where the loads are, and you can test it at an upper load and a lower load, and you can kind of infer a lot of times what the behavior is going to be inside. Well, software is more like a Seurat painting. It's this pointillist kind of system where almost all over the place you have discontinuities. And so the testing results you have at one point make no difference at all to the behavior that you have at a different point. It's almost an analogy. It's a rough analogy. Imagine you're building a bridge. Thank you. And you want to test the load, so you put some grad students on it because they're light and you can get new ones. And it holds up. And then you put 20 dump trucks on the bridge and everything looks good. And then 2 Thursdays from now, a yellow Volkswagen drives down and the whole thing collapses. It's that there are these discontinuities in where the behaviors lie that make it very difficult to test. So we think of software as being a cloud. We make bugs. We make mistakes at different points. And when we run tests, there are these little points, 1,000 points of light. Well, you can run 1,000,000 points of light. It doesn't matter. Because even small software systems have trillions and trillions of possible states. So you need to step back. I mean, software testing is good, and we do it rigorously. But we really need something stronger. And so what we've been working on for the last 20 years, actually, at the University of Minnesota and places like Honeywell and Rockwell Collins, is the application of formal methods of proof to software. So software is no different than any other piece of math. It has a lot more cases, usually. But you can apply the same proof techniques that you would do in any mathematics course on software, because ultimately it is a formal object. So in our approach, we had proofs of memory safety. These are the ways that people usually sneak in for the critical control components. We had proofs of partitioning, meaning that the operating system always does what it's supposed to. And the part that the University of Minnesota focused on was the system architectural proofs. So given that you have these proofs of software components and the operating system, how can you scale that to say something reasonable about the entire system? So I'm going to give you a total toy that has nothing to do with security at all. But for you math geeks out there, you might like it. So the interesting thing, this is kind of an example of what compositional verification is. At each level of the system, you make certain assumptions about the inputs to that level. And then you want to prove certain guarantees about the outputs at that level. And in between, you have subcomponents that implement different pieces. And they have their own assumptions and guarantees. So in this particular system, we have an assumption that the input is less than 10. And the question is the output less than 50? And it turns out that you can prove this sometimes. So if you assume that the types you're dealing with are integers, then this is actually provable given these facts about the subcomponents. But if you're dealing with real numbers, it's, in fact, falsifiable. So having tools that allow you to do this compositional verification in a sound and scalable way is absolutely critical. And that's the work that we've been up to. So just to make this more relevant to security, imagine that this is an encryption piece. This is a routing piece that determines where the data goes within the automobile. And this is the actual controller that controls your brakes. So you'd want all of these three things to be working in tandem in such a way that you had confidence about only trusted commands can cause the brakes to work. So here's just a little bit of what it actually looks like. This is more of an eye chart. If you can read this, good. You don't need glasses yet. But it's a little example of the cruise controller where you talk about expectations in terms of inputs. You expect the speed to be greater than 0 and less than 150 miles an hour. This is not a Formula One car. And then we have some guarantees about how the cruise control is going to work. Now, imagine this at scale. So when we did this work on a medical device, or when we did this on the DARPA project, we were looking at hundreds of requirements in giant contracts. And the proofs ran for hours, but this is actually a big improvement over not running at all. And it wouldn't matter if, at the end of the day, we could just do the proofs. So what's the impact? Well, the impact is it worked great. We were able to keep the red team entirely out. They had access to all of our information. They had 3 months, and essentially a team of 6 people who had world-class experience, and they were not able to get in. This was entirely unexpected. DARPA thought that perhaps we could keep the red team out for a week or 2, and that would be a success. But it was entirely on a different scale. And the good news is that math still works. And when you apply proof to software, it works just as well as it does for materials or anything else. And we had 3 phases, and in each phase we secured more of the vehicle. And by the end of the phase, we had most of the vehicle secured. And for those surfaces, no vulnerabilities were found. So this was a big deal. And being an academic, I try and turn in my homework 2 or 3 times, or as many as I can get away with. And so the tools are now used in my graduate software engineering class. Thank you. Some people in the audience were using earlier versions of the tools. It didn't work so well. So thank you for helping be guinea pigs. We've used this on medical devices. We're trying to work with the medical community here in town to apply this at more scale. We've applied this on the helicopter, on smaller helicopters. The ground team, which was separate from us, ended up using our tools because they worked. And we've also applied this to the 787 and business and regional jets and other things. We had a story on 60 Minutes. That was exciting. And the big thing was in 2015, Ash Carter, then the Secretary of Defense, we got him to say formal methods. So that's a big step. Because normally they don't want to hear anything about that. So I think there's a bright future of this kind of technology, and it's a good thing because software is now in charge of things that can kill you in lots of different ways. And that critical software is being networked in ways that it never was before. So now we're not talking about single vehicles, we're talking about autonomous vehicles or fleets of autonomous vehicles where they might coordinate how the traffic lights work. Well, what could go wrong there? There was a gentleman who came and talked at our meeting in 2015, and we said, well, what's your security story? And they said, well, we're still working on it. I said, yeah, okay, well, I'm not buying one of those. Anyway, the brunt of the work was obviously not done by me, but it was done by this group up here at Boeing and Rockwell Collins and Data 61 and other people, and my very talented graduate students in the Crisis Lab, and Mats Heimdall, who's the department head, computer science there. There's a lot more information on this. It's, I think, fascinating, and we have videos and other things that demonstrate the attacks and the defenses against them if you want to go out here. But thank you very much for your time and attention.
Well, I think everybody would agree that that was just fasciterrifying. Or it might have been terra-fascinating. I'm really not quite sure, but I'm going to be extremely careful driving home. So I think that was a delightful set of remarkably diverse, but each in their own way, amazingly compelling discussions of what's going on in this college and what it means to the community. So with that, we're going to go to questions. I'm going to kick it off with a single question, and while I'm doing that, please, if you have questions, think of them soon. We're running slightly over time, but we're going to take a little bit of time and do this, if that's okay. We'll finish at about 8, if that's all right. So I'm going to just kick it off by saying, just very briefly, what attracted you to the University of Minnesota, and why do you stay here, along with a little bit on your interaction with students and how they're involved with your work? So, Cathy, we'll start with you. What attracted me was, back then, the civil engineering building was a new building. It was a brand new laboratory. The faculty who were here were great. I
I'm originally from Minnesota, which is a strong connection too. I think a lot of people were talking earlier. If you're from Minnesota, you go elsewhere. Usually you like to come back to Minnesota. And just the resources in the Twin Cities with the laboratory industry professional network is fantastic.
Terrific.
I've only been at the university for a little over 2 years now. Before that, for 30 plus years, I was with Honeywell in town the whole time in the Twin Cities area. And I'd often thought for the last 20 years, actually, that ultimately I should end up in academia. That's where I belong. That's where my industry colleagues think I belong. So, but then some things, opportunities seemed to arise, or things were changing, and so I said, now is probably the time. And the question is, how do I go about this, or what should I do? And I put one constraint on myself, and that was I did not want to leave the Twin Cities. So after having been here 30 years, I'm not from here, but somehow, I've sort of don't have family here either, actually, but nonetheless, just really like the region. So but there's only one major research university in the Twin Cities, and I was fortunate. I ended up with thanks to some colleagues and the head of the institute I'm with, Professor Masood Amin. I ended up at the University of Minnesota, and I have a Honeywell chair at the University of Minnesota. So it made it easier to write the resignation letters. I'm leaving Honeywell, but I'm taking up a Honeywell chair. Yeah. So, and no regrets. The program I lead, in fact, great to see a couple of students who just graduated just last month from our program. Our students are working full-time, and they come to campus 1 day a week, a Friday or a Saturday, while term is in session. And pretty intensive program, as they'll tell you, but they're so motivated, and they're so hardworking, and it's just a joy to be in the environment.
Yeah. Well, I've taken kind of this circuitous path through both academia and industry. I got my PhD here. I'm born and raised in Minnesota. My parents are sitting right here. Then I really enjoyed both. But I was working in an industrial context where I was working on kind of short-term problems. And actually, you have less control over what you get to do. So I was being asked to actually apply some of the formal methods in maybe an attack mode rather than a defense mode. And I'm like, I don't want to do that. So my former advisor, current department head, made me an offer I couldn't refuse. And so I ended up here at Minnesota. And I also run a master's program with also wonderful, amazing students who also work full-time. But ours is a software engineering-focused program. And they are inspiring. The people do interesting things that I would have never come up with. So there was an IoT class that they were working on. IoT also scares the pants out of me for security reasons. Mm-hmm. But they came up with a portable air quality sensor that if people use would be like Google Maps, but for air quality. And if you're in a major metropolis in Delhi or other places, it could really make a difference in how you work. And so they're going to actually pitch this to start up a company. These are rare opportunities. These are rare students. And the graduate students I work with in the PhD program are equally stellar. They're from all over the world, and they come here to work on, and they're better at math than me, to work on really interesting problems.
Very good. All right, we have time for a couple of questions from the audience, and we're going to go up here. We got a couple of people. Go ahead.
Is your name Cathy? Is that
Yes.
Hi. I was once in Kiev, and the Golden Gates of Kiev is rumored to be made out of eggs. The mortar, they put eggs in the mortar, and it made it impervious. They still stand. They've been up there for like 1,000 years. Is there any truth in that, or do you know anything about protein mixed with concrete?
No, but I have heard there are some interesting combinations too with the Great Wall of China and things as well. But I'm not so certain about the material aspects of that, so I'm not sure.
Okay. All right. Go ahead. Back here, and then there'll be one right here. We're going to sneak 3 questions in.
I'm Dale Thomas. I'm a 1985 graduate of the Civil Engineering Department and had Professor French as in one of her first classes at the U. And I had a question about this striving to get the next tallest, longest span, everything else. Obviously, we have the technology to do those things, but how likely is it we're going to have another Galloping Gertie? I mean, the Millennium Tower in San Francisco is leaning, and there are examples of things that have fallen. How likely is it that the technology is going to be exceeded again?
That's a great question. And so there are always issues. I think like when you look at the Millennium Tower in San Francisco, that's a case where a structure is now deflected into the ground quite a bit and also is leaning quite a bit. And there, it was a foundation issue. There's a lot of complication, even in the Twin Cities, when you look at some of the buildings that we have in stadiums. There's old riverbeds that go through. So part of some of the stadiums are built on solid bedrock. Part of those are built on poor soils where there was a riverbed going through. And to try and see below the surface, they do borings and things like that. But sometimes I think better solutions could have been done if there was some foresight with some of those problems. There are some things that I would say are not good decisions. So you can't control those types of things. But how we look at design is we try and make sure that our capacity that we have, the capacities that we know, are the structural properties, the material characteristics, that we can determine those pretty well. I'd say where we end up usually having problems that are out of our control is with the demand. So for example, as climate change is happening and that the loads are going on our hydraulic structures, the pipe demands, the things like that associated with those environmental effects on our structures, those are some of the things that are going to be more challenging. When is the next big earthquake? What will that magnitude be? I'd say even the Northridge Earthquake of 1994, people never thought of the large vertical component. There were a lot of failures because of that large vertical component. So we try and limit the possibility for failure, but you can never guarantee something 100%, but we want to make sure that that likelihood is very, very small. And I'd say the biggest challenge is in the demand side, that uncertainty.
Okay, one more question over here.
I guess I'd like to ask a concrete question, but actually would go to all the other speakers as well. How do you deal with failure over time? And because all these things are going to change, how long do you expect the building to last, made of whatever it is? But anyway, you get the general question. You have talked about the current, but you haven't talked about what's going to happen over time.
So I'd say one of those things, and that's an excellent comment too, is when you look at even bridges, people are designing for a 100-year life. And when you look at the amount of money that's going to the infrastructure, it's very low. But if you think of your car, if you have a car and you never change the oil or you don't maintain it, what happens is things are going to deteriorate. So I think the biggest issue is we need to invest in our infrastructure to preserve those structures. So I think that's a huge issue, and one where I think if you spend a little bit along the way to keep things in well condition, over time they'll last longer rather than if you let them deteriorate, you're going to have a lot more expensive task on replacing things in the future.
And I guess I'll just say that I think, of course, all systems, all devices ultimately will fail, and the question is how can you predict them and how can you mitigate that? And I don't think there's any sort of silver bullet I can cite. I think modeling has a big role to play, and being able to collect data while things are working and being able to extrapolate from the data. So the ability to have low-cost sensors, pervasive sensors, I think is, and analytic platforms could be something that could help with that issue.
Yeah, and I don't know anything about real things. I know a lot about software. So it's interesting because software, in one sense, it either always fails or it never fails. There are certain inputs that will cause it to fail consistently, and there are certain inputs that will cause it to work forever. However, software is generally embedded into a larger construct that is changing all the time. So we build formats for images or things. And those formats are changing all the time. So you wrote a document in WordPerfect in 1994. Good luck getting that off anything. And that's really a concern, is the long-term archival data formats, because what happens is that our industry is moving so fast, and there's so little thought to backwards compatibility that we're running away from relatively recent things that we've constructed.
That's important for all fields. We have data, massive data too, and as those formats change, it's a huge challenge. But
it's more of in a way, it's more crucial, I think, in the digital space than the analog space. Who uses microfiches anymore, right? But still, if you had a microfiche, you could do something. You would be able. It's analog. You could do something with it, right? Vinyl, very similarly. But you have some encoding that's lost, and the translation mechanism is lost, and that's
All right, and with that, we just want to say thank you for attending this. There are light refreshments out in the lobby, and please stick around for a while. And thank you.